Hello everyone. Again, my name is Filip Marić, and I'm a PhD candidate at the University of Toronto STARS Lab, jointly with Lamor at the University of Zagreb. And my talk today is titled "A Geometric Approach for Generating Feasible Configurations of Robotic Manipulators." And kind of the goal of my talk will be to summarize the research in my PhD thesis and kind of to give an idea of the types of problems I've encountered and the tools I've used while trying to solve these problems. And so, as the title suggests, my research has mostly been motivated by problems in robot manipulation. And with this in mind, I think it makes sense to start this talk by noting that to manipulate means to make an intentional change in the environment through selective contact or motion. And this definition is, of course, quite general, but it gives an indication as to how important manipulation actually is. And in fact, most living organisms, regardless of their complexity, perform actions involving some form of manipulation. For example, very simple life forms, such as bacteria, use flagella to navigate and manipulate their surroundings. Various rodents, such as hamsters, use their limbs to store large and unreasonably large chunks of food in their mouth. And closer to us in the evolutionary tree, primates have been observed using simple tools such as stones and sticks to break apart shells and measure the depth of bodies of water. One second. So, in fact, one of the things that make humans so special is, in fact, our high capacity to skillfully perform these manipulation tasks. This capability enabled us to develop kind of a variety of tools and techniques that eventually landed us on top of the food chain, despite the fact that we were physically inferior in comparison to most of the prey that we hunted. And this really kickstarted a sort of positive feedback loop of technological development, where we leveraged our manipulation skills to create a larger surplus of resources that increased our population and lifespan, which then enabled us to create even more advanced tools and so on. And of course, since this development relied on tedious manual labor, the idea of getting someone else to do the work for us was kind of a powerful driving force throughout human history. And in this context, the idea of robots comes quite naturally. In fact, the word robot itself was introduced in a 1920 play by Karl Čapek, and it comes from the word rabota, which means servitude or drudgery. And actually, we have been very successful at developing robots tailored for specific tasks in controlled environments. These industrial robots greatly increased the production output in industries that traditionally required large numbers of line workers, such as the automotive industry. However, it has become clear that one of the crucial next steps in our technological advancement involves the development of general-purpose robot manipulators, which would be used in tasks requiring autonomous and collaborative manipulation, as well as intelligent teleoperation. These tasks will take place in dynamic and unpredictable environments, which would require manipulators to be governed by a high degree of artificial intelligence. And really, the research I will be presenting is motivated by the need for these general purpose robotic manipulators, and is done on these types of manipulators. So these robots consist of a series of revolute joints with a single rotation axis. And these axes are connected by rigid links, thereby forming what's known as a kinematic chain. And at the end of this chain is a tool, usually a gripper, also known as an end effector, that is attached to the final joint. And in most applications involving manipulators such as these, researchers and practitioners need to find joint configurations or motions that are required to perform these tasks. And this is really the central problem addressed in the field of robot kinematics, which studies how changing joint configurations affects the movement of a robot's links. So let me first introduce some of the core problems in robot kinematics. First, let's consider this open serial kinematic chain that is a simple 3-joint robot such as this. So given some configuration vector theta representing the state of the joints, which is usually their angle, our goal is to find the corresponding task space vector xi, which is generally the pose of the end effector or some other link. But for our purposes, we will always consider it to be the end effector. This procedure is known as forward kinematics, and this forward kinematic mapping is generally nonlinear. However, it has a simple derivation of its analytical expression, and there exists a unique solution for any input into this mapping. However, applications such as reaching, grasping, and servoing that we usually think of when thinking of autonomous manipulation generally require us to find configurations that correspond to some desired end effector pose. And this procedure is known as inverse kinematics. 1 second. All right, as inverse kinematics. Ideally, we would simply analytically invert the forward kinematic mapping, but this is difficult, and general solution strategies for this really only exist for robots with up to 6 degrees of freedom, that is up to 6 joints. Further, depending on the goal, there may be an infinite finite number of solutions or even no solutions at all. And so this problem is generally approached using local optimization techniques. And these optimization-based approaches can be related to the problem of differential kinematics, which looks at the relations between end effector and joint velocities. Here we consider the derivative of forward kinematics with respect to joint angles. And this derivative is known as the manipulator Jacobian matrix, and it gives a linear approximation of the relationship between the change in configuration and change in end effector pose. Crucially, this system can be solved for a desired target end effector velocity using a simple quadratic program whose solution is basically the Jacobian pseudo-inverse. So clearly, by solving this system, we can find joint velocities that achieve a target end effector velocity. This procedure is known as kinematic or task space control, and variants of this are commonly used in manipulation tasks. In fact, by considering velocities to be position deltas, we basically can retrieve a variant of gradient descent that allows us to solve inverse kinematics by incrementally guiding the robot towards the goal. This approach is commonly known as closed loop inverse kinematics, and it gives an insight into how optimization-based methods operate for this particular problem. So in summary, finding joint configurations required to complete a particular task requires us to define the problem using a desired end effector pose and various other constraints such as obstacle avoidance, and then encoding these constraints into a local optimization problem, which is then solved using one of the common solution methods, depending on the problem characteristics. And then the solution, that is the joint configuration, can be checked for constraint violations by passing it back through forward kinematics. And so finally, this brings me to my first research problem, which is known as singularity avoidance. So if we remember the Jacobian identity earlier that we used to control the movement of the end effector in the task space, either by directly setting the desired velocities or tracking a reference pose in a closed loop, we could use this, of course, to control the robot. However, just naively implementing this, eventually we would likely come across situations such as the ones shown on the right. Here you can see that in both videos, the robot exhibits this rapid and unstable movement when attempting to follow this reference path. And assuming that the assigned task space velocities are reasonable, we can conclude that the Jacobian is in fact numerically unstable. We can analyze the Jacobian by performing singular value decomposition and monitoring its singular values as the robot follows the assigned path. And in the case of the robot on the right, we notice that one or more of the singular values would drop to 0 or near 0. Configurations that cause such bad Jacobian matrix conditioning are known as singularities. So clearly we don't like singularities. They generate rapid and unsafe movement of a robot's links. At a singular configuration, the robot completely loses a degree of freedom, while even being in proximity to singularities results in the robot requiring large joint movements in order to perform relatively small motions with the end effector. So they're kind of really bad overall. Luckily, it turns out that we can use geometric reasoning to develop intuitive singularity avoidance indices that can be optimized as part of control and motion planning algorithms. So we start by self-multiplying both sides of the Jacobian identity I showed earlier, and we would arrive at this kind of geometrical interpretation of Jacobian conditioning. So first, we could equate the right side of this equation with a unit sphere in the space of joint velocities. And then we can interpret the left side of the equation as basically the mapping of this sphere into the task space. And this sphere maps into the task space in the form of an ellipsoid. And this ellipsoid is known as the manipulability ellipsoid, and its shape and size are strictly a function of the robot's Jacobian at a given configuration. So the capacity of joint movements to produce motion in the task space direction is proportional to the lengths of the manipulability ellipsoid's axes. In fact, these lengths are exactly equal to the squared singular values of the manipulator's Jacobian, which gives a clear geometrical interpretation of its conditioning. This interpretation has previously been used to develop indices which are optimized as part of planning and control algorithms. So first we have the manipulability index, which is proportional to the volume of the manipulability ellipsoid itself. And it's often used with gradient-based optimization methods. And another common index is the so-called dexterity index that geometrically can be interpreted as measuring the elongation of the ellipsoid, because it's basically the ratio of the length of the longest and the shortest ellipsoid axis. However, the problem with these indices is they don't give a full insight into the ellipsoid's geometry, and this results in some crucial blind spots. So for example, looking at these two ellipsoids right here, we see that the red and blue ellipsoid are of a different size, but of the same shape. So they have the same ratio of the longest and the shortest axis. And this is exactly what causes the dexterity index not to be able to differentiate between these two. So the dexterity index for both of these ellipsoids would be identical. However, the manipulability index would, of course, be able to differentiate between the two because it measures the volume. On the other hand, here we have a situation where we have two ellipsoids of the same volume, but a drastically different shape. And we see that the red ellipsoid here actually has one axis that is kind of undesirably short, or has an undesirably low magnitude, indicating that the robot would have trouble moving in that direction. However, the manipulability index could not differentiate between the two ellipsoids as they have the same volume. So clearly, to really get the proximity to a singularity, it would be best to infer it by accounting for the manipulability ellipsoid's full shape, which is difficult to translate into optimization criteria. And this leads us to an interesting idea. So if there was a notion of a differentiable distance between two ellipsoids, could we derive an optimization criteria that minimizes the distance between the current manipulability ellipsoid and some sufficiently non-singular ellipsoid? For example, we could set a reference ellipsoid of a spherical shape that is always larger than the current manipulability ellipsoid. And thereby, in an optimization scheme, we could try and minimize this distance to force the current ellipsoid to expand towards this larger spherical ellipsoid. However, since ellipsoids are described by symmetric positive definite matrices, we cannot simply take the Euclidean distance between two of these matrices. In fact, ellipsoids form a convex cone in the vector space of symmetric matrices, and they are not a vector space in themselves. However, it turns out that this set describes a Riemannian manifold, where a geometrically appropriate distance can, in fact, be defined. And this geometric description has already been used and allowed us to reason about the differences between two ellipsoids. It has recently been shown that this characterization can be used to successfully perform manipulability ellipsoid tracking and transfer. And building on this work, we derived a differentiable geometry-aware singularity index, which is defined as the squared Riemannian distance between the current manipulability ellipsoid and the larger spherical ellipsoid enveloping it. And this geometry-aware singularity index can then be easily added to most control and inverse kinematics algorithms. For example, we can minimize the distance by adding the gradient of the geometry-aware singularity index to the objective function of this basic kinematic control quadratic program. However, the computation of this gradient is also an important contribution of this work, since it in itself is non-trivial to derive for an arbitrary choice of a reference ellipsoid. And the way we tested this index is we imagined a task where a robot or three different robots had to follow a circular path in their task space. And this circular path would usually lead them through some sort of near singular or singular configuration. And the idea is that we would try to traverse this path by minimizing our index, by maximizing manipulability, and by just looking at what happens when we don't do anything. And here you can see the two rows representing the top row being the lowest singular value of the Jacobian, and the bottom row being the highest singular value of the Jacobian, measured throughout the robot traversing this circle. The dashed line represents the baseline in this case, and we can see that for the UR10, the robot actually passes through two singularities when singularity avoidance is not accounted for. On the other hand, standard manipulability maximization manages, of course, to avoid these singularities. However, we see that, and the standard manipulability maximization here being shown in red, while our method, which is shown in blue, has the highest overall lowest singular value of all methods. So it really means that our method keeps the robot as far as furthest from singular configurations compared to other methods. In gray, also, it's interesting to note that we have a variant of our index, which uses a Euclidean distance. And clearly here, it can be seen that it doesn't do nearly as well as when a proper Riemannian distance is used. And so this paper is associated, the paper associated with this work is published in the Robotics and Autonomous Systems Journal, and there are several other related works we've published as conferences, so feel free to check them out if you're interested. So overall, what this research has shown is that associating a specific geometry with a problem will give you interesting results. And we have a singularity index that's based on the length of the geodesic between the current manipulability ellipsoid and the reference ellipsoid. We show that it can be easily differentiated with respect to joint values and easily integrated into existing IK and control formulations. And so before moving on, let's zoom back out and take a look at this general pipeline for solving inverse kinematics using optimization. So repeating everything, we see that first we defined a problem by setting a desired end effector pose and constraints. These are translated into constraints for local optimization problem, which is, of course, defined over the space of joint configurations. And then the solution, this is solved using some nonlinear optimization approach. And then the solution is checked by passing everything through forward kinematics. However, we can kind of consider why this optimization problem can become difficult by noting that the decision variable itself is the configuration, and it lies in the configuration space. While most common constraints, such as those enforcing a specific end effector pose or obstacle avoidance, lie in the task space. And as mentioned before, the mapping between these spaces is the nonlinear forward kinematics mapping, which, of course, which ends up being the source of some of these problems with singularities, with these local optimization methods ending up in local minima, and so on. So maybe if a different geometry could be associated with this problem, it might enable us to have both the constraints and the decision variables in the same space, which might make the optimization somewhat more favorable in certain cases. And so this question brought me to my second research problem of distance geometric robot kinematics. And here we have some previous work by Porta that showed, quite importantly, that the configuration space of a few specific robots can be represented by Euclidean distance matrices, or EDMs. And inverse kinematics can be solved by algebraically finding missing matrix elements. And this is really interesting because Porta's result hinted at the fact that IK might be in some way equivalent to the distance geometry problem, which unifies problems such as sensor network localization or molecular conformation. And really fitting the IK problem in this paradigm would unlock a large variety of techniques that could not be used previously. And more importantly, it would open up the possibility of defining the IK problem within a single space, as opposed to having a distinct configuration and task space. And our first step, since previous work only gave examples for some specific robots that could be solved, for which this thing could be solved in closed form, our first contribution here was developing kind of an algorithmic approach for constructing distance matrices describing robotic manipulators given their structural information. And in short, this is done by placing a pair of points on the rotation axes of the robot's joints and the z-axis of the end effector coordinate frame. And using this, we could form a graph of interpoint distances. And if we have all of the distances, this graph and the resulting distance matrix, we were able to prove that there exists a unique mapping to the corresponding robot configuration. So there would be no two distance matrices or two interpoint distance graphs that would result in the same configuration. However, the thing of interest for us here is that this description also allowed us to define an inverse kinematics problem. So here I will give a simple example of how this is done. So first, we have the pairs of points associated with the rotation axis of each assigned coordinate system, or each rotating joint, as well as some additional points used to model the base coordinate system. And on the left, we can see that all these distances define some off-diagonal elements of the distance matrix. And the diagonal elements, of course, are all zero because they correspond to the distances of points to themselves. Since we also know the link geometries, because the robots have rigid links, we can fill out a bunch of other off-diagonal elements with the distances describing the robot structure. And this structure can be retrieved either from a URDF file or DH parameters or any other parameterization of the robot's geometry. And so the important thing here is that you could now imagine this graph being attached to this robot, and you could really move every joint now. You could rotate it any which way. However, the actual distance matrix, the defined elements in this distance matrix would not change. The only elements that would change would be the ones that are currently marked as question marks. And this is already quite interesting in itself, but it becomes even more interesting when you consider the inverse kinematics problem. Because with the inverse kinematics problem, what we also have is a definition of the end effector pose. And this, since we would then know the end effector pose, would give us an additional set of distances that we could add to this matrix. And so if we could find these missing elements, we would complete the distance matrix. And then there would be a straightforward procedure of retrieving the point positions from these distances. And then again, a straightforward procedure of retrieving joint angles from these points. And really, our research has shown that this approach kind of seamlessly allows for a variety of constraints, such as link poses, constraints such as obstacles and symmetric joint limits. Most notably, obstacles are important here because they can be included as spheres defined by points whose distances from the robot are lower bounded, and thus really they are just additional elements in the distance matrix and nothing else. Right. So now we still have the question of how to find these missing elements, right? We've pushed the inverse kinematics problem into this problem of missing EDM elements, and now there's a question of, okay, so how do we find them? And we can kind of get to a general optimization framework for completing these matrices by looking at how a distance matrix is actually constructed from matrices containing the point sets. And as you can see here, if we arrange our point sets into matrices, we can obtain what's known as a Gram matrix using a simple matrix product. And then the distance matrix can actually be computed using a simple linear identity. However, note that the rank of the Gram matrix will always be equal to the embedding dimension of the underlying collection of points describing the robot. So the rank of the Gram matrix for most robots would be 3 because these robots are described as a set of 3-dimensional points. And this suggests that EDM completion can be formulated as a local optimization problem over the manifold of Gram matrices of fixed rank. So even though this problem is quadratic and seems at first sight to be relatively simple, the problem here is that we've kind of pushed this complexity into restricting where our decision variable can actually be. So it's also important to note here that in this problem, it's sometimes confusing. This matrix omega is just used to select the constant elements of the distance matrix that describes our structure and the problem, and to make it correspond to the distance matrix that we've computed from our Gram matrix. And so naturally, this formulation can also be extended to include distance ranges by adding constraints or other elements to the cost function. Right. Okay, so we somehow need to implicitly constrain the Gram matrix to the Gram matrix rank, and we do this by factorizing this matrix back into point matrices, thereby getting a quartic problem, which is of course less convenient. And next, since the cost function depends only on distances, we wouldn't really directly optimize over points, and rather we would try and optimize over the equivalence class of point sets up to a rotation or reflection, because we don't care how the entire set is rotated or reflected as long as the interpoint distances are the same. And again, it turns out that this can be done by using results from Riemannian geometry, which showed that this is in fact a quotient manifold that we can move on during the optimization process. And using this result, we can efficiently use a variety of optimization methods to solve this problem. So kind of an overview of this would be, we would define the problem as an incomplete Euclidean distance matrix, which can also be visualized as an incomplete graph. And then we would perform an optimization that would serve to find the remaining distances, or the remaining elements of this matrix, or complete the graph, right? And then we could, from this complete distance matrix, we could retrieve the point set, and from the point set, we could retrieve the joint angles and extract the joint configuration, check for constraint violations. And given that both obstacles and decision variables here would lie in the same space, we would expect that approaches based on the distance model would recover solutions more easily than conventional approaches. And to test this hypothesis, we set up this kind of simple experiment where several common manipulators are located in highly restrictive environments. So as you can see, there's really a lot of obstacles here that make it difficult to find feasible configurations. And looking at these results, We have two rows here. The top row shows the success rate over 1,000 inverse kinematics problems, and the bottom row shows the solution times, while the columns represent the different environments. And as you can see, in terms of success rate, our method here shown in red outperforms the method shown in blue, which is just a regular joint-based local optimization approach. However, it does, if we look at the lower row, it does take somewhat more time to solve the problem. But this changes once obstacles are introduced, and then our method actually remains at a relatively constant solution time, while the joint-based method ends up taking a lot more time and having a larger drop in success rate compared to our approach. And again, kind of the conclusion of this is that associating a specific geometry with a problem gives interesting results. We've extended the distance-based IK formulation to a wider class of robots and constraints. We provided a formal proof of the equivalence between the distance geometry problem and an extended class of inverse kinematics problems. We also used the generic Riemannian optimization method to solve the distance-based inverse kinematics problem. And the paper associated with this contribution was published in the Transactions in Robotics journal. We also published several other papers on this topic in Robotics and Automation Letters and various conferences. I would also like to note here that most of this research was done in collaboration with my colleague from STARS Lab, Matthew Gamu, and we spent a lot of time working on all of these publications together. And yeah, so now kind of taking a step back again, we can see that regardless of the advantages provided by a specific representation, all approaches based on numerical optimization share kind of the same fundamental limitations. Importantly, they can only return a single solution when, in most cases, there would exist infinitely many, and there's generally a trade-off between success rate and solution time. Also, the recovered solution and the convergence of these methods heavily depend on the initialization that's used. So a specific knowledge is necessary to enforce certain types of solutions. So naturally, kind of these limitations have motivated the use of deep learning to train models that find feasible configurations for a given robot subject to a set of task space constraints. So in this case, such models would generally take a problem description as an input and transform it into some form of feature vector. And this feature vector would then be propagated through this multi-layer perceptron, and the output of this would be used to infer a joint configuration. The resulting configuration could either be used as part of a optimization, as an initialization for an optimization algorithm, or as a solution directly. Unfortunately, the fixed input and output shapes, as well as the fixed ordering of the features in these vectors, limit their generalization capacity, which means basically that really these models can only learn solutions for one particular robot. So you train them for one specific robot. And kind of the single input output nature of standard supervised learning makes capturing entire solution sets infeasible in this form. So these are kind of the two limitations that one observes when thinking about deep learning for inverse kinematics. And in this case, it's clear that local optimization is in many ways superior because it's usually faster, it's less opaque than these learned models. And so there's really not much reason to use them. And this brings me to the final segment of my talk, which is my most recent research on generative graph inverse kinematics that I'm performing in collaboration with Oliver Limoyo from STARS Lab. And at this point, let's again recall that the distance-based IK formulation I talked about earlier makes the IK problem equivalent to other so-called distance geometry problems, such as molecular conformation and sensor network localization. And so while I was doing this research, I came upon papers on these other instances of distance geometry problems. And one of them was the problem of molecular conformation or protein folding that kind of shared this property of there being a large number of valid solutions to a given set of these distance constraints. And lately, some notable results, such as those obtained by the now famous AlphaFold, indicate that there may be learning architectures that lend themselves to generalizing to different robots by way of graph-based representations. And really, since we've shown that the distance-based IK problem admits a graph representation, it really follows that it is in principle compatible with graph neural networks, or GNNs. And these are architectures that have given interesting results in related distance geometry problems. So we decided to explore whether implementing this type of architecture would give interesting results in inverse kinematics. And the core advantage of GNNs is that they have an increased input and output capacity compared to regular models due to them being defined over graph structured data. That is, each node in a graph that's used as an input or an output of a GNN is associated with a fixed size feature vector. But the network itself generalizes to graphs of arbitrary shape and size and connectivity, which means that, okay, the feature vectors for nodes are fixed, but you can plug in any graph you want. And why this happens is because what GNNs do is they kind of behave like message passing networks, where a message between two connected nodes is computed by an MLP using the features associated with the nodes and perhaps the feature of the edge connecting these nodes as well. And all the messages pertaining to a given node are then aggregated and used to update the node feature. So by using this distance-based representation of the IK problem together with the graph-in, graph-out nature of the GNN, we have kind of circumvented the first limitation that we talked about, where now we have a model that can be trained on a mixed data set of different robots. So here you would have, let's say, a partial graph as an input, passed through a GNN, and then have a complete graph as an output of the model. So really, we've kind of unlocked a set of models that can be trained on this mixed data set and maybe generalized in a certain way. However, using this deep learning to solve this problem still doesn't have many of the advantages over optimization, since even this model can still only output a single solution. And okay, so having this basic idea in place, we then thought, how can we find an architecture that helps us surmount this other limitation? And we landed on kind of we decided on a generative network architecture. And we landed on the idea of the graph conditional variational autoencoder, which basically learns a latent space distribution over random configurations together with a conditional prior over a partially complete graph representing the associated IK problem. So how it goes at training time is basically the upper part of the network. So here we have a GNN encoder. It takes in a full graph representing some specific robot configuration. It outputs a distribution, which is then sampled and decoded by the GNN. And the idea here would be to reconstruct that same configuration. While the bottom network, which is the prior, it actually takes a partial graph that represents an IK problem that this partial graph this partial graph represents an IK problem that this particular configuration is a solution to. And what we do at training time is we try and minimize the difference using KL divergence between these two distributions. So we have this distribution that's used for reconstruction and this distribution that encodes these partial graphs. And we're trying to make them as similar as possible. And the reason we are doing this is basically because then at test time, if these distributions are close enough, if everything is trained correctly, what you can do is you can just feed a partial graph representing the IK problem into a GNN encoder, sample this distribution, pass it to the decoder, and get a configuration that solves the problem. But then what you can also do is you can take more samples and pass them again, and ideally get different solutions. And in theory, this solves both of these kind of core limitations, right? And it is our belief that by solving these two things, you kind of make a deep learning approach towards inverse kinematics feasible, or at least interesting, and we give it some concrete advantages over local optimization. And indeed, when we do a forward pass of this model, here you can see in the top row, we have some examples of inverse kinematics problems. So just imagine the end effector pose here being the definition of the problem, and we're trying to find a configuration that solves it. So the top row here is what you would get with, let's say, using a local optimization approach, while the bottom row is what you get when our network is used. So here you see you get an entire distribution of solutions that all solve this IK problem. And then the question is, okay, how accurate is this? And surprisingly, our latest results show that this is quite accurate. It gives solutions that are really close to the target pose. And here we trained just a single model on 5 different robots. So again, single robot on a mixed data set of 5 different robots. And the mean position error of the solution was approximately 5 millimeters, while the mean rotation error was in the range of half a degree. The one outlier here is the Panda robot, which is this one, which has a structure that's somewhat different from the other 3 robots, and we believe that made it kind of underrepresented in the data set. So the model ended up generalizing more between the other 4 robots. And in fact, we've tested this by training a version of our model directly on the Panda. And we got a result that's here in the top row that basically shows that we get errors in the range of position errors in the range of 3 millimeters and rotation errors that are lower than half a degree. And this allowed us to compare directly to a very recent paper that uses a normalizing float type architecture to learn solution sets for individual robots. And we've outperformed that architecture as well. So this research is currently available as a preprint on arXiv. We will soon submit it somewhere, and we also will soon update this preprint with our latest results. So in conclusion here, the geometric inductive biases in learned models gave us, again, interesting results. It allowed for more diverse training sets enabled by the input-output flexibility of GNNs, the ability of sampling from a distribution of configurations conditioned by desired pose carries the possibility of improving existing motion planning algorithms that are based on sampling configuration. And of course, this distance geometric formulation allows us to further integrate obstacles into this entire scheme, as well as other task space constraints. And it might enable further generalization. It might enable sampling collision-free configurations. And okay, so finally, just a conclusion, maybe some takeaways that are fairly generic, but there it is. The first one is associating novel geometries with existing problems may add, subtract, or change their properties. Different problem properties will often allow us to use different tools and solution methods that may be more suited to a particular application. And in learning, prior geometric information can be used to imbue architectures with useful inductive biases. And perhaps most importantly, and this is something that I came to as kind of like a core point of my PhD, is that choosing a good problem geometry is really as important as choosing the optimization method or learning architecture. These are the related publications. And finally, I would like to thank all of my friends in L'Amour and Stars Lab for really making this entire PhD experience rewarding and fun and great. Also my deck committee and Ivan and Jonathan for really kind of helping me navigate this entire joint PhD situation. It wasn't easy. It definitely wasn't easy at times, and without your support, I couldn't have done it. Thank you.
Outstanding. Thank you, sir. Very nice. do a virtual clap on Zoom. Wonderful. Yeah, I think part of the debatable. The research is certainly technically very challenging. The administration of a joint PhD across 2 continents is also substantially tricky. I think maybe you should get a PhD in both. Actually, we should give you 2. Yeah. Okay, so I think wonderful presentation. That's fantastic. Thank you, sir. We have a few minutes for questions. We have about 6 or 7 minutes if folks would like to ask. And we'll just open the floor. Yes, maybe stick up your hand. So, Filip, the other Filip, go ahead.
Hey, incredible presentation. It was fantastic. And yeah, I was really impressed by your latest results. And I was wondering how easy or hard would it be to integrate this work into like common motion planning frameworks like Move It, for instance, with Ross. I think for the first part of the talk, it was sort of obvious that you could simply integrate this into the IK, like track IK maybe. But for the second part of the talk, I was wondering how easy or hard would it be to use that for motion planning?
Right. So I think for motion planning specifically, the first next step that we need to do, and it's actually really a shame that, well, there wasn't enough time to do it, maybe later, was to extend this architecture to include obstacles, right? So if we were able to get a situation where we could train distribution that samples collision-free configurations, then this becomes very interesting, right? Because here motion planning algorithms then may benefit a lot. There's some work that does this type of thing, but it's not, I think if we got the types of results we're getting for this, for obstacle avoidance, we could make some sort of, just a network that does the sampling part and integrate it into existing motion planning algorithms. I'm very kind of optimistic about that. I think it's a very kind of, it might result in very interesting things down the road.
Great, thank you. I'm gonna be following your work closely then.
Thanks.
Excellent, thank you. Collaborator on the left of my screen, Boston Matt.
Hey, Boston Matt.
Great job, Filip. That was wonderful. Great presentation. I wanted to ask about combining the sort of 2 first ideas. So what do you think about representing singularities or manipulability or something related in the sort of distance geometric framework? Have you had any thoughts on that approach?
Yeah, that's a really good question. So again, the first thing that would have to be done there is you would need to get essentially you would need to try and define the Jacobian identity, like redefine the fundamental Jacobian identity that's used in the joint formulation, where you have end effector velocity equals Jacobian times joint velocities, right? You would need to redefine that somehow to be defined in terms of distances, right? So then your configuration space would be, since it's all the same space, you would need to somehow have a situation where you have the distances that are constant are your configuration vector, and then you have the Jacobian of the difference between the constant element in the distance matrix and the constant elements in the distance matrix and the distance matrix produced by these distance elements. So you take that Jacobian and you would have to define this velocity in the space of distances. So it's like a distance space velocity. And then you would have a Jacobian, right? And when you have a Jacobian, it's again like this idea kind of generalizes in a way, right? It's just that your directions would be directions in the space of distances, right? So, but manipulability and dexterity and whatever, it would all translate. These are just basically general tools for matrix conditioning and for improving matrix conditioning, right? So yeah, I thought about that quite a bit. Yeah, but I'm not sure. I was never like super attracted to the idea of going down that road, just because I'm not sure whether we would get anything better than what's currently done with the joint stuff, but maybe not. I don't know. It is an interesting idea.
Other questions? Anyone? Oh, Professor Delutario. Welcome. Great to see you.
Well, thank you. It's been very, very kind of you to say. Actually, I will save my questions until after your next presentation, which I understand is pretty soon. I only wanted to chime in and commend you on a really nice and clear presentation. It was really nice listening to it.
Thank you very much.
Thank you. Very excellent. Most excellent. Thank you. Okay, we're just right at the 11 o'clock hour here, local Toronto. We have maybe time for just one more question if there is one, but if not, no worries. We will.
I could sneak one in if that's all right.
Yeah, sure. Of course, go ahead. For sure.
Yeah, so I guess first of all, Philip, got to echo everyone else, really enjoyable presentation. I wanted to ask, so for this is sort of maybe a general inverse kinematics question. So for that sort of work, how sort of, if at all, does your sort of inverse kinematics problem setups and solutions, how does that change in, I guess, the relatively common case when, if I'm like looking at a whole trajectory of some sort that I want to plan where, you know, the next solution is going to be very close or should definitely be very close to the current solution. What should I like, how do things change then? Am I just saying like, okay, this is a good initial guess for the next one and the problem becomes easier? Do I sort of switch to a local method for a while and use yours as sort of waypoints? Like, do you have any sort of, you know, what should I be doing there just to, you know, get good solutions in terms of computation time, things like that?
Yeah, that's an excellent observation. I think, yeah, in the sense when you're following some sort of a trajectory and you know that your current state is close to the solution of whatever the target and effector pose is, I think in that case, reverting to the simplest possible approach is usually best. With there are a few caveats there. So, of course, generally, I would just use the straight up the Jacobian identity I showed at the beginning, right? You really usually just need a first order iteration to get you, like one or two iterations to get you to the next place. As long as you're satisfied with the next configuration being really similar to the current configuration, because that's what's going to happen, right? You're going to the pseudo inverse scheme is by definition, it minimizes joint movement. So it tries to minimize how much you move. So what can happen is if suddenly and for some reason you want your next solution to be different, you want your next solution to be radically different, and then you wouldn't use your current state as an initialization. You would use something else, right? And here then, especially if there's some additional constraints, obstacles and such, here you might want to use a distance-based formulation, because that might give you kind of a radically different solution, because there's nothing, there might be nothing forcing it to stay close to the current configuration, right?
Makes sense. Yeah, thanks a lot.
Thank you.
It's an excellent question also. Thank you. Perfect question to end on. All right. Okay. Thanks, everyone. So I don't see any further questions. And I think that was a great one to end the talk with.